Hello everyone, welcome to the first of a short series of videos I'm going to make on waves. The first video is going to be on transverse waves. We'll go through longitudinal waves and a few other things, two-dimensional waves and things like that in another video. But this video I want to focus on transverse waves, what they are, how they work, a few things about them. So to start off with, I'm going to do some demos with a slinky here to try and demonstrate what a transverse wave is and a few of the properties of transverse waves. So to start off, the definition of a transverse wave is one where the wave is moving in one direction, but the actual disturbance of the things is perpendicular to that. So when I send a wave down a slinky, the wave is going to travel towards that chair and back, but the actual bits of the slinky, none of them are going to travel forward and back, they're only going to travel up and down. Looks like this. Just steady this out. Okay, transverse wave. That's a transverse wave. Notice that I pulled the slinky up, and then all the way along the slinky, the bits of the slinky were moving up and down, but the entire wave was moving forwards. So look at that again, and this time focus on just a point on the slinky that I've marked here. This little point with a little elastic bow tie here. When you look at that point in the transverse wave, even though you can see the wave going forward and back very clearly, the elastic band itself will not go forward and back. It'll just go up and down. So again, here's that example. Okay, there it is. I'm actually going to let a little bit of extra slinky out here so it travels slightly slower. Do that one more time. There it is. The elastic band itself is not traveling forward or back. Okay, so that's a transverse wave. Transverse wave travels along the slinky. It's going, the disturbance is up and down. That makes it a transverse wave. Now when we look at this transverse wave, when it gets to the other side, it's fastened to a chair over there, so it can't really move. And if you notice, when I send the wave along the first time, the wave was traveling along on the top of the slinky. When it hits that side and comes back, however, you'll notice that the wave is traveling along the bottom of the slinky. So again, watch carefully for that. On the way towards the chair, the wave is on top of the slinky. On the way back from the chair, it's underneath. So keep an eye on that. Go. Try and make it a little more obvious there. There we go. So again, when the wave bounces off of a fixed surface like this, it ends up coming back on the other side on the way back. So again, this is a transverse wave. Now, what I want you to think about is if I take this wave and I send one wave towards the chair, it bounces off and comes back this way. But if I send a second wave at just the right time, when the wave comes back this way, if I send a second wave that's in the same direction, you're going to have one wave traveling along this way and one wave traveling along underneath like this. When they meet each other, because there's an up wave and a down wave, they cancel each other out, the wave will kind of cancel. However, if I sent two waves that were both up waves towards each other, when they meet, they make a bigger wave. So imagine then that I take this slinky and I send an up wave down the slinky and it's going to come back underneath. So while it's coming back underneath, I'm going to send a down wave. So the down wave coming back and the down wave going forward are going to meet at the same time and make a big down wave. That's great. Now when my down wave hits that side, it'll come back as an up wave. And this one will come back as an up wave. They'll both be up waves. Then both down waves, then both up waves. So the whole thing, if I do that just right, is actually real simple. It just looks like this. I'm sending up and down waves that are reinforcing each other when they bounce off the far side. So I send an up wave, then it comes back as a down wave and meets the down wave that I'm sending, and on and on. This is called a standing wave. You'll notice that the points at the end, at my hand and the chair, are both fixed. They don't move. Whereas the point in the middle is doing a lot of movement. It's traveling a lot. The point in the middle is called an antinode, and the 2 points that aren't moving are called nodes. Now, if I do this a little bit quicker, when you send waves a little bit faster, their frequency increases, and it turns out what that does is it decreases the wavelength. It makes the waves shorter. So if I make this twice as fast, hold up, gotta struggling. There it is. What you'll notice is that there's actually, whoops, losing it. There's actually two places where the waves are going up and down quite a lot. And three places now, one at my end, one in the middle, and one at the chair, that are not moving at all. Now, what I have here is a machine that sends those waves for me so that it doesn't have to be me doing that terrible demonstration. So what we're going to start with here is the machine is vibrating so that it sends 8 waves per second down this string. At the other end, we have a weight here that just holds it fixed. This is a standing wave, just like that first standing wave I did with the slinky. It's sending an up wave, then the down wave is coming back as this one sends a down wave, and then the up waves meet and the down waves meet, and they keep on bouncing back and forth like this. This is our first standing wave. Has 2 nodes and 1 antinode. Now, again, if I go twice as fast, so if I speed this thing up to 16, what we see is the wavelength is shorter. It's half as long. So here, it's sending an up wave, it goes down wave, it bounces off here, there's an up and a down, and it reinforces the waves that are coming from both ends. So again, we get an antinode, or we get a node in the middle where there's no motion, and an antinode over here where there's tons of motion, lots of up and down. Okay, so this is our first resonant frequency. This is our first harmonic of the standing wave that we had last time. Now, some interesting things happen on a standing wave. The node is really stationary here. It's not moving at all. And so what you can do is you could hang something on it. If you get it in just the right place, like so, it doesn't disturb the wave even slightly. It sits there vibrating, and this bit doesn't vibrate at all. You can hang something on it, it's no big deal. You can touch your finger to it, no big deal. The wave keeps going. If you try and do that somewhere else, if you try and touch your finger to it here, notice how the whole wave kind of collapses. So, standing wave. Node, antinode, node, antinode, node, vibrates back and forth. You have reinforcing waves here and waves that cancel each other out here. Now, the words for that we're going to use in the future are when 2 waves reinforce each other. That's called constructive interference, okay? When they cancel each other out, that's destructive interference. It is not deconstructive, it is destructive. So destructive and constructive interference, canceling each other out, reinforcing each other, big waves. Now, as we speed this up, if we go to any other multiples of 8, like, 24, now again, we're going to get an extra set of waves. The wavelength shortens. We get our constructive interference, making antinodes, and our destructive interference, making our nodes. And we can do this for any frequency that's a multiple of 8. So if I speed this thing up to, let's say, 48 hertz, well, 48 is 6 times 8. So we're going to have 1, 2, 3, 4, 5, 6 antinodes. And anytime there's 6 antinodes, there has to be 1 extra, so 7 nodes. And this is one of the many harmonics of that first frequency. Okay, now there is one other thing to notice here. When you're watching this video, you may not see a nice smooth pattern here. You may see a kind of highlighted rope traveling back and forth along this that seems a little bit funny. And that's actually the same effect you see in a lot of situations, but what's happening is the camera on my computer is only recording this in snapshots. It's not a continuous recording, right? It's recording this one picture every 60 seconds. So it's only taking pictures every 60th of a second, and that's why you see a line that's floating up and down. It's called a beat frequency, and hopefully we'll talk a lot about that in the future. Okay, so that's it for transverse waves. We saw the transverse waves and how they work, and then we saw a standing wave, which is simply a transverse wave which is trapped between two objects and reinforces itself and cancels itself out at certain points to make antinodes and nodes with constructive or destructive interference. That's going to be it for transverse waves. I'll be back in a while with longitudinal waves. Thank you.